Okay, so this is section 3.8, and what we're doing in this section is talking about implicit differentiation. Okay, so this is something that I think is worthwhile to go through more than once and to definitely practice, because I know that historically students, this is the hardest part, or not the hardest necessarily, but it's one of the hardest parts of this chapter. Okay, so we're going to go through this in detail, and hopefully it'll make sense, and we'll have some examples. Before we get to implicit differentiation, though, it's all built on the chain rule. So what we're going to do is begin by reviewing the chain rule. Okay, so here's our statement of the chain rule. If I have a function h of x that's defined as the composition f with g of x plugged in, then the derivative of h is f prime with g plugged in times g prime of x. Okay, and just like we saw in class, we can write this using Leibniz notation. If I replace the g of x with a u, and if I replace the composition f of g of x with a y, then y is f of u, and the derivative of y with respect to x is the derivative of f with respect to u times the derivative of u with respect to x. Okay, so let's look at an example here. So suppose y is sine of x cubed. Find the derivative dy dx. Okay, so using our regular notation, I could say, all right, when I differentiate, I get y prime. My outside function is sine. This x cubed is the inside. So when we differentiate, we say, all right, the derivative of sine of stuff is cosine of stuff. The chain rule says plug in the inside function, so it's cosine of x cubed times the derivative of x cubed. And the derivative of x cubed is 3x squared. So we have cosine of x cubed times 3x squared. Okay. The way to do this same problem using Leibniz notation okay, the inside function is x cubed, so I could write u equals x cubed, and my outside function y is sine of that stuff, so y is sine of u. Okay, so then if I differentiate du dx, the derivative of x cubed is 3x squared. If I differentiate sine of u, dy du is cosine u, right? So if u is my variable, then the derivative of sine u is just cosine u. Okay, so then the derivative of y with respect to x is dy du times du dx, and I already have those pieces. Dy du is cosine u, du dx is 3x squared, and I can replace my u now with the x cubed so that I'm down to just one variable. So this is cosine of x cubed times 3x squared. Okay. Now, the Leibniz notation I don't think is helpful when we're just doing chain rule problems. This seems more complicated to me, okay, and probably to you also. The point is not that it helps with just these straight chain rule problems. It'll help going forward, right? Recognizing these pieces and using this notation is useful, because what I can do is I can look at taking a derivative where my variable is x and also taking a derivative with my variable is u, and that's what we're going to need later on in this section. Okay, so that's our quick review of the chain rule. Now let's talk about implicit functions. So what we have here is comparison of two different graphs. Okay. Oh. No, my background's going crazy. All right, that's all right. What we have here is a comparison of two different graphs. On the left, we have y equals x squared, a parabola. This is a normal function. And on the right, x squared plus y squared equals 1. That's a circle. And unfortunately, the circle is not a function because it doesn't pass the vertical line test. Okay, the parabola passes the vertical line test. And this seems a little bit unfair. These are both a very simple shape, but because the parabola I can write as a function because it passes the vertical line test, I can do all of my calculus on. And because the circle fails the vertical line test, is not a function, I can do none of my calculus on. And I feel like that seems unfair. And it seems like a real limitation, right? If an object as simple as a circle is too complicated for calculus, then that seems like calculus is kind of weak, right? So what we want to do is be able to do calculus on both, and we need to get around this idea, or this limitation of the circle not being a function. Okay, so the way that we're going to do this is with something called an implicit function, right? So if instead of looking at the whole graph, if we just zoomed in and we looked at a piece of the circle, right? So if I go back up here to the graph, and you say, well, you know, if I look at some point on the graph and I just sort of zoom in around it, okay, if all I looked at was inside this brown box, inside here, the graph looks like a function. So if I limited myself to just that piece of the graph, then I could think of this as being a function, and then I can do all my calculus stuff. And that's really the idea of an implicit function. If a graph looks like a function in a small space, then I can do calculus at that point, okay? And we could think of the calculus as moving around, right? If at a different point, maybe I need a different zoom in window, okay? But it also looks like a function over here. So I can think of my calculus as kind of working around point by point and you know, being able to do things like find a derivative at all of those points. Even if the graph as a whole is not a function, the pieces of it are. All right. So that's what we do with implicit. That's what an implicit function is, right? So if the graph looks like a function, passes the vertical line test, in some small neighborhood around a point, like a zoomed in box, then we call the graph an implicit function. And then we can do all of our calculus at that point. So just to give you maybe a little bit of an example, I'm going to take a funny looking graph. Right? And if I pick a point on the graph, say here, I can find a zoom window around that point that looks like a function. But if I pick a point, say at the very edge, and I take any zoom window I like, I'm always going to fail the vertical line test. Or if I pick right here in the middle, again, any zoom window around that origin point is always going to fail the vertical line test. Okay, so these points are hopeless. Okay, so with implicit functions, there still may be points where we can't differentiate. And that's going to be points where I have like a vertical tangent or where the graph crosses over itself, because even if I zoom in, I won't be able to make it look like a function. So it's not going to work at that point. Okay, but all of the other points on the graph it does work at. Okay, so that's still okay. We can deal with a couple of bad points instead of, you know, throwing out the whole graph. So now let's look at how do we do the calculus? How do I actually differentiate? Right? So here's the general idea. When we differentiate, we think of y as a function of x. But since it's an implicit function, I don't have a formula for y. I just know somehow that y is a function of x. Okay, so what we're going to do is we're going to just sort of differentiate away, right? When I take a regular derivative, we take the derivative of both sides. We don't think about it, but if I write like y equals x cubed, then when I take a derivative, on the left, I rewrite the y as y prime, and then I use my derivative formulas on the x cubed. Okay, and okay, that's what we're going to do here. We're just going to differentiate both sides. Okay, so let's look at what that looks like. Okay, so I'm going to look at this equation, x squared plus y squared equals 4. Just to give you some reference, we don't normally draw the graph of implicit functions, but for something like this we can. Right, so I'm going to get a circle of radius 4, and we want to find the tangent line when x is 1. Now, before I get started, one thing I'll notice on the graph is that when x is 1, I'm going to have two different tangent lines. I should have drawn my circle a little more neatly at the bottom. But I'll get another tangent line down here. Okay, so knowing just the x value often isn't specific enough for an implicit function. Often we're going to need an x and a y value. But if I have just an x, we'll figure out how to deal with that in a minute. So let's look at how do I do the derivative part of this. Okay, so I'm going to start by writing my relation here, x squared plus y squared equals 4. And now I'm going to differentiate both sides. So on the left, when I differentiate x squared, the derivative of x squared is 2x, no big deal. To differentiate the y squared, the y is my inside function. So I'm using the chain rule. My outside function is stuff squared, so the derivative of stuff squared is 2 inside stuff to the power of 1. My inside function is y, and then the chain rule says multiply by the derivative of the inside function. Well, if my inside function is y, the derivative is the derivative of y, dy dx. And then I also differentiate the right-hand side of the equation, right? And the derivative of 4, right, that's constant on its own, is 0. Okay. So now I'm done differentiating, but I don't really have like a formula for my derivative. Now I have to solve for dy dx. Okay. So I'm going to subtract 2x on both sides. So we have 2y times dy dx equals negative 2x. And then I'm going to divide both sides by 2y. Okay, so now we have dy dx equals, the 2's will cancel, so I just get negative x over y. One of the things I want you to notice here is that my derivative formula requires, or has both an x and a y in it. So to find a slope, I need to know both x and y. And that makes some sense when we look at the graph. In order to find a slope of a tangent line, just knowing x isn't enough, because if I'm on the graph and x is 1, I could have this negative slope or I could have this positive slope. So I need to also know what y is, right? So what we do is we say, all right, let's break that down. Let's find y. Okay, so when x is 1, I have 1 squared plus y squared equals 4. 1 squared is 1, so subtract both 1 from both sides, so y squared is 3. So y could be positive or negative square root of 3. Okay, so if I want to find the tangent line, I'm going to treat the 2 points separately. Okay, so we have at the point 1 comma root 3, and we have at the point 1 comma negative root 3. Okay, so at 1 comma root 3, the slope is the derivative when I plug in 1 for x and root 3 for y. Okay, so the way that I can write that is I can write this as dy dx, and then I put a vertical bar that means with x equals 1 and y equals root 3. Okay, so then I get negative 1 over root 3 as my slope. Okay, so then the point slope of the line will be y minus root 3 equals negative 1 over root 3 times x minus 1. Okay. If I want to write this in slope-intercept form, I can distribute this negative 1 over root 3. So I get negative 1 over root 3x plus 1 over root 3, and then add root 3 to both sides. So I get y equals negative 1 over root 3x plus 1 over root 3 plus root 3. And we're not going to clean it up any further than that. Just leave that. Okay. But I notice that I get a negative slope at 1 root 3. And that, again, sort of lines up with our graph at 1 root 3. The tangent line is sloped down a little bit. Okay. So then at 1 comma negative root 3, the slope is the derivative where I plug in x as 1 and I plug in y as negative root 3. So I get negative 1 over negative root 3, which gives me a positive 1 over root 3. Okay, so then the equation of the tangent line is y minus negative, right? So y plus root 3 equals 1 over root 3 x minus 1. So distribute, and I get 1 over root 3x minus 1 over root 3, and then subtract the root 3 from both sides. So y is 1 over root 3x minus 1 over root 3 minus root 3. And here I can see, okay, I have a positive slope, and again, that lines up with the little graph that we drew. All right, so this was an example of implicit differentiation. What I want to do now is sort of make this a little more formal and look at some more challenging questions. So here's our process. In the last example, we really illustrated this step 1, right? Differentiate both sides, be mindful of the variable, right? So if x is a variable, anything else is a function of x, and we use the chain rule, okay? If dy dx, though, shows up in more than one spot, it can be a little bit of a challenge to solve for. So the rest of these steps walk you through that. Gather all the dy dx terms on one side of the equation, and we can factor it out, and then we solve by dividing. So let me go through those steps in this next example, and you'll see what this is all about. So I have this new function, x cubed times sine of y plus y equals 4x plus 3, and I want to find dy dx. So we're not going to mess with the equation of the tangent line. We're just going to look at finding the derivative portion of this. Okay, and I have to be very careful at the beginning here. X cubed is a function, sine of y is a function. I'm multiplying these functions, so here I have to use the product rule. Okay, so let's go ahead and differentiate, and I'm going to be very step-by-step about this. Okay, so when we use the product rule, we take the derivative of the first piece, so the derivative of x cubed, times the second piece, sine y left alone, plus the first piece left alone, times the derivative of the second piece. Okay, so that's the setup for my product rule. Then I have to differentiate y. The derivative of y is the derivative of y, which we write as dy dx. On the right-hand side, when I differentiate 4x, I get 4. When I differentiate a constant on its own, I get 0. Okay. So now we're going to walk through the rest of this very carefully. The derivative of x cubed is 3x squared. just going to recopy down the sine y, recopy down the x cubed, and now I have to differentiate sine y, and here the y is my inside function. So when I differentiate sine of stuff, I get cosine of stuff. Chain rule says plug in the inside function, and then multiply by the derivative of the inside function. The derivative of y is dy dx. And now we'll just copy down the rest of the equation that we have written down. And now I can see dy dx shows up in more than one spot, and this is why we have these steps listed out. So step 2, gather all the dy dx terms on one side. They are on one side, but I want to get everything else to the other side, right? So I'm going to subtract 3x squared sine y to move it to the other side. Okay. So now I have x cubed cosine y times dy dx plus dy dx equals 4 minus 3x squared sine y. And then what we're going to do is we're going to go ahead and factor the dy dx out of the left-hand side. Right? That's that step 3. So if I factor out dy dx, what I'm left with is x cubed cosine y plus 1. And that factoring out is the way to separate the dy dx from everything else. So now I can solve for dy dx by just dividing. So dy dx equals 4 minus 3x squared sine y over x cubed cosine y plus 1. Okay, so that's an example of implicit differentiation. Any questions so far?
Can you keep it there for a second?
Okay, well, there's not a whole lot more to it, but I want to make sure that, you know, we kind of figure out what's going on. So we're going to do a couple more examples. Our next example is going to be finding the second derivative, and that one can be a little bit confusing. So I'm going to, you know, we have to be careful about second derivatives. The second derivative is the derivative of the first derivative. So what we're going to do to begin with is to find the first derivative. Okay, so I'm going to start with x squared plus y squared equals 4, and I want to find the derivative dy dx. Okay, and we went through this. This is a circle of radius 2, so we did something just like this a minute ago, but let's go ahead and work it out. So when I differentiate both sides, the derivative of x squared is 2x. For the derivative of y squared, the y is my inside function. Okay, so I have 2 inside stuff to the power of 1. The inside function is y, and I multiply by the derivative of the inside function. The derivative of y is dy dx. Okay, and then the derivative of 4 is 0. So 2x plus 2y dy dx equals 0. I'm going to subtract 2x from both sides. So 2y dy dx equals negative 2x. And then I'm going to divide both sides by 2y. So dy dx is negative x over y. So this is our first derivative. To find the second derivative, what we do is we take the first derivative and we differentiate it. So to find second derivative, d squared y dx squared, we're going to start with the derivative, dy dx equals negative x over y, and now differentiate. Okay, so on the left, when I take the derivative of the first derivative, I get the second derivative. On the right, to take the derivative, I have to use the quotient rule. So writing out the quotient rule, we have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay, so when I take the derivative of the opposite of x, I just get -1. Minus a negative we can write as plus x, and the derivative of y is dy dx. Okay, so now I have the second derivative, but I don't just have two variables. I don't just have an x and y. I have kind of three. I also have this dy dx in there. Okay, and having x and y makes sense, but having the dy dx in here seems a little unnecessary. But I have a formula for it, right? I know that dy dx is equal to -x over y. So we can replace dy dx with its formula, which for this problem is -x over y. So second derivative is -y plus x times -x over y all over y squared. Okay, and to simplify this, because I don't like fractions within a fraction, I'm going to multiply by y in the numerator and denominator. So when I distribute that y, I'm going to have a -y squared. Then I have a minus. X times x is x squared, and the y over y cancel. And then the y in the denominator will give me a y cubed. Okay. So this is good enough. You could stop here, although it does simplify one step further, because if I look at my original equation, x squared plus y squared is 4. So if I factor a negative out, I'll have negative x squared plus y squared, which is equal to 4. So I could write this as -4 over y cubed. So that's kind of a very, very simplified version of the second derivative. All right, so that's finding a second derivative with implicit differentiation. Let's look at one more example where we're finding an equation of a tangent line. Here we have a more complicated graph, and I'm going to show you a little trick you can do if we're not interested in the derivative, we're just interested in the slope of a tangent line. Okay, so I'm going to start by differentiating this. Let's write out y cubed plus x cubed minus 3xy equals 0. And when I go to differentiate this, this is in the y cubed, the y is my inside function. And over here, I can think of this as plus a negative 3x times y. That's a product rule. Okay, so I'm just planning out the pieces of this as we go. So now when I differentiate it, I'm going to use the chain rule. So the derivative of stuff cubed is 3 stuff squared. My inside function is y, and then the chain rule says multiply by the derivative of the inside function. The derivative of y is dy dx. X cubed, I don't need a chain rule on. That's the derivative of x cubed is just 3x squared, because x is my variable here. Okay, now I have a product rule. So I want the derivative of -3x times y left alone plus -3x left alone times the derivative of y. Okay, and now let's, as a separate step, work out those pieces. The derivative of -3x is -3. The derivative of y is dy dx. Okay, and then everything else we just copy down. So we have 3y squared dy dx plus 3x squared. Okay, now we could solve for dy dx using the steps that we had before, and that's fine. That would work perfectly well here. But if all I'm interested in is one slope of the tangent line, what I would do is I would solve for dy dx, and then I would plug in for x and for y. I can do that before solving for dy dx. We can do this now, okay? So now that the differentiation is done, we're free to plug in if we like. So if I plug in x is 3/2 and y is 3/2, then instead of having the derivative as a function, I instead have, at one point, I just have a slope. So I'm going to plug in x is 3/2, y is 3/2, and now instead of having a derivative, I have a slope. So we have 3 times 3/2 squared times m plus 3 times 3/2 squared minus 3 times 3/2 minus 3 times 3/2 times m equals 0. And the point of this is that it's generally easier to do algebra with just numbers and one variable than it is with 3 variables. Okay. So when I square 3/2, I'm going to get 9/4 times 3 is 27/4. Same thing here, 27/4 minus 9/2 minus 9/2 m equals 0. Let's just make everything have the same denominator. So multiply by 2/2. Okay. So 27/4 m plus 27/4 minus 18/4 minus 18/4 m equals 0. Okay. 27/4 m minus 18/4 m. 27 minus 18 gives me 9. So we have 9/4 m. And then 27/4 minus 18/4 is, same deal. And I get 9/4. So 9/4 m equals 9/4. So m equals 1. So now when I go to write the equation of my tangent line, I have y minus 3/2 equals 1 times x minus 3/2. So I can ignore the 1, add 3/2 to both sides, and I just get y equals x. All right, any questions over this?
Why'd you do a chain rule in the beginning?
Okay, so that's implicit differentiation.
Why'd you do chain rule in the beginning?